Okay, there we go. So we've got a block size of 64, and once we know that, the next thing that we need to do is we need to count off our network IDs based on the block size of 64. And so we start with 0. So 0, next we've got 64, next we've got 128, and next we have 192, okay? All right. So those are our network IDs. And based on this, then, I can now start to build my table with my network ID, my first address, my last address, my broadcast address, and I can even go so far as to put out there my CIDR value. So there's my network ID. And there are my 4 networks, okay? So from here, I need to figure out what my first address is for each one of these network IDs. And it's always going, the first is always going to be one more than the network ID. So we're going to do a 1, we're going to do a 65, we're going to do a 129, we're going to do a 193. Now, we're going to figure out what our broadcast addresses are. And the broadcasts are always going to be one less than the next network ID. So in our first example, the next network ID is 64. So we're going to do one less than 64, which is going to be 63. And then we're going to do 127. And we're going to do 191. And here, because we're at the very top, this is going to be 255, okay? The last thing we're going to do is we're going to figure out what our last address is. And last address is always one less than the broadcast address. So we've got 62, we've got 126, we've got 190, and we've got 254. And then the last column that we want, our CIDR, is going to be how many bits, how many subnet bits are there for each one of these addresses. And because it's a fixed length subnet mask problem, all of the subnets are going to have the same number of subnet bits. So, hey, Greg, how are you tonight? So our answer here is going to be 26. 26. How was your Thanksgiving?
It was good. How was yours?
Very nice. Thank you. 26. Okay. So there is the answer to our fixed length subnet problem. And before, what I want to do is I want to do one more of these, unless you want me to do more than that. But I'd like to do one more. Before we jump into that, Greg, is there anything specific that you'd like me to hit on this evening?
No, I watched the video of the Saturday one. I couldn't make it. I was on my way to Newark dropping my son off. So
yeah, no problem. No problem.
But I watched the video. No, there was a couple things, but I mean, it was basically I did like the part where you did the explanation of the actual, like, the Ethernet frame versus the IP set,
right?
IP packet versus the segment versus the datagram. It was kind of good. Like, you see them in a row, and the explanation actually made sense. That was really good versus looking in the book. And,
yeah, if you actually look at the fields, and you know, in a test, we tend to hurry a little bit. But if you look at the fields through common sense, you can kind of figure out what's what.
Yeah. But there's a couple things when you get to the datagram versus the segment. Oh, and then also that chart you had. I don't know where you got that from, but that was it. It gave all the OSI layers versus.
Right.
It was that chart was great. And is that available, or is that because I don't know, that was different than the normal CIBEX PowerPoints.
Okay, well, I'll tell you what. Yes, that was my chart. So
yeah, that was really good because that kind of like showed you the difference between the OSI and then where the segments versus packets, and where the different devices sit. That chart was fantastic. That with those other things with the breakdown of the other pieces.
Sure.
Was really good.
Yeah, I developed that a while ago. I don't know why I didn't share that with your class, but this is what you were referring to.
Yeah. Okay. And then the only other thing I was thinking of, and I have it written down somewhere, I just dig it out, is how to crack into the router or going into the configuration or whatever to like reset the password, because we only did it one time. So
well, I'll tell you what. I'll be happy to go over that. However, I am not going to have that on the test.
Okay.
There will be. I will have some questions about it, about changing the configuration register.
Right, yeah. So I mean, we only did it one time, and so it's like it's something that didn't really sink in too well. So I mean, I could dig through my notes and find it.
Okay.
Because that's not in the book, is it?
It's actually in the book. I believe it is chapter. I believe it's chapter 7.
Okay, chapter 7.
Yeah, one moment. Let me see if I can open that up.
Yeah, this diagram is really good. I really like this. Now it actually makes sense. You can see it at a different angle.
Right. Yeah, it kind of summarizes it pretty quickly. Let me get out to my Canvas site and just pull this up. Okay, so here we've got courses, and we've got 235, and we've got PowerPoint, and I'm pretty sure it was chapter 7.
Yeah, it's funny how many people wanted. I see the vote went towards extending the exam to next Thursday.
Yes.
But yet I see that the attendance is quite light on these. And Sharin's a double. He was there on Saturday, and so it's like, he's got an extension, but nobody's on the line here.
Yeah. Sometimes I don't know. Maybe it's actually chapter 6. But I'll tell you what. I'm going to keep that in my list of things to go over. But let's go back and let's finish with the subnetting. Okay, but that's good to know, and we will hit that this evening. All right. So let's bring this up. Okay, there we go. So. Okay. So in our next problem, we're going to essentially take the same address up here. Only this time, I want to do 5 subnets rather than just 4. And this is going to basically force us into a slightly different type of problem. Again, we will use our formula up here. And so we've got 24 network bits and we've got 8 host bits. We're going to use the formula 2 raised to the power of the number of borrowed host bits. So the question is, how many bits must we borrow in order to get the number of subnets that we need? Now we need 5 subnets, okay? Well, if we substitute for x and we use x is equal to 2, then it's going to be 2 to the 2 is equal to 4. And 4 is not enough for 5. So the next value of x will be 3. So in this problem, it will be 2 to the 3, which is going to be 8. So in order to make this work, we're going to have to borrow 3 bits. So let's just visualize that. And again, we're going to ask that question, what's the block size? What is the value of the rightmost network or subnet bit? Thank you, Sharon. I could count on you for that. 32. All right, so we've got 32. So what's our next step, gang? What do we do from here? Patrick, what do I do next? Maybe Patrick stepped away. Okay, still online. He's out there. Okay, yes, we're going to basically do go in jumps of 32, starting with 0. So I've got 0, 32, 64, 96, 128. And remember, I only need 5. Okay, so after 128, I've got 160, then 192, and I'm just going to keep going just for kicks. 224, and that would be the last one, and that would then hit the top address of 255. But we only need the first 5, so we're going to put in our. Let's go back and let's steal that. Let's take this, copy it, bring it down. So let's put our network IDs down: 0, 32, 64, 96, 128, and 160. Now, I added in the 160 simply because it's going to help me in my calculations. I only need these first 5, all right? So we put in our first host address, always one more than the network ID. So 1, 33, 65, 97, 129, okay? And I don't need this here, okay? Or I don't need to really use that here. It's only in the broadcast that we really need it. And we're going to go over to our broadcast. And again, the broadcast address is always one less than the next network ID. So we've got 32, so one less than that is 31, 64, come on, 64, 95, 127, and because I've got this 160 here, it makes this a lot easier to figure out, 159, okay? Then our last address, one less than the broadcast, so 30, 63, 94, 126, and 158. Okay. All right. So And again, okay, Patrick, tell me what my CIDR is going to be, if you would, please. Uh-oh. Okay. I see you guys are jumping on me. Sorry, 63. Thank you. 62. I'm like, what's going on over here? There was a riot over on my chat session. Okay. So correct. Okay, my broadcast should have been 63. And the thing that should have really keyed me off here as a double check, okay? Again, your network IDs are always going to be odd, or I'm sorry, even. Your first address is always odd. Your last address is always going to be even. Your broadcast address is always odd. Okay? So if you quickly scan that, and so what happened, Sharon was looking through this, and she noticed that I put in 64, and it should have been an odd number. So that right there was the clue that this was not right. Okay? So nice job, gang. So again, Patrick, what is going to be our CIDR value for this thing? Sweet. Good job. Okay, and again, what we're doing is just look here. And if we count all this up, I've got 8, 8, 8, and then 3. So 3 times 8, that's 24, plus 3 more, that's 27. So all of these are going to be a /27. Okay? Is that good for everybody? Any questions? Okay, very good. Good. Patrick, do you think you want me to do a third one, or is this good? Do you want to move on to variable length subnet masks? Okay, very good. We will move on. So Vlsm is what we're going to work on next. And I'm going to write the rules over here that you should follow. So the first step is to identify the number of networks. And the second is how many hosts are needed for each network. Okay? So I'm going to tell you over here what we need. So A is going to need 2. B is going to need 116. C is going to need 12. And D is going to need 59. Okay? So we've answered the first 2 questions. 1, how many networks? And there are 4 networks. The next question, how many hosts are needed for each network? A is 2, B is 116, C is 12, and D is 59. The third thing that we need to do in descending order. Okay, order the networks in order of the number of hosts in descending order. So if that's the case, the largest one is going first. Okay, so that's actually going to be network B, and it has 116. Next is going to be D, and it has 59. Then C, that has 12. And then finally, we've got A, and that has 2. So that's the network number, if you will. This is the number of hosts. And from here, we need to determine what is the block size that is needed for each one of these networks. And the block has to be big enough to hold the number of hosts. Now, a block is one of the powers of 2. Okay, so we start with, 2, 4, 8, 16, 32, 64, 128. Okay, so in order to hold network B, what is the block size that I'm going to need for network B? I'm going to need 128. Thank you, Sharon. All right. And Patrick, what is the block size I'm going to need for D? Very good, 64. Greg, how about C? Okay, 16, perfect. And then finally, I'm going to need 4. I'll take the easy one. I need 4 for network A. All right, perfect. Now we need to start figuring out network IDs. So our network ID, always with the first one, is going to start with 0. Then we're going to add the block size from the prior plus the network ID to give us the next network ID. So 128 plus 0 is 128. Next, we're going to do 64 plus 128, and that's going to give us 196. No, I'm sorry, 192. Okay. And then finally, I'm going to do 16 plus 192. And what is that going to give me? Okay, 196. Check again. 208. Okay, very good. Thank you, Patrick. So 208. And if I go one more, 4 plus 208 gives me 212. Okay. And so let's continue with these 4. Determine the block size. 5. Create your network IDs. 6. Okay. Calculate the first host addresses, and that's what we're going to do now. So my first host address for each one of these. So one more than the network ID. So I've got a 1 here. I've got a 129 here, a 193 here, 193, a 209, and I don't need to do this one. And next we've got last, but we'll hold off on that just a moment. Let's come over here, and we want to do broadcast, and we want to do the CIDR column. And the broadcast is always going to be 1 less than the next network ID, which in this case is 128. So this is going to be 127. This is going to be 191. This is going to be 207. Come on. There we go. And the reason we wrote this 112 down here was just to help us with this value, 211. And now we're going to do our last host address. So let's just continue to fill this in. Okay, then 8. Last addresses, I'm not consistent with my capitalization, so please forgive me. Last address is always going to be one less than the broadcast, so we've got 126. And again, you know, your last addresses are always going to be even, okay? 190, 206, 210. Okay. Sharon, do you want to tell me what my CIDR is going to be for network B? Okay, very good, /25. Patrick, how about for network D? Sweet, 26. Good job. All right, Greg? 28. Very good. And the last, okay, is going to be a /30. Okay. So there is our answer for VLSM. Okay. Questions? Go ahead, Patrick. You have a question? Okay. Correct. Okay. And specifically, it pertains to version 4 addresses. Okay. IP version 4 addresses. The beautiful thing about variable length in comparison to fixed length is fixed length subnet masks do not efficiently allocate IP addresses in terms of the number of addresses. Okay, every network gets the same number of host addresses. And if we look at like a network such as A, which only needs 2 hosts, and I'm handing out 32 addresses for that address or for that network, it really doesn't make much sense because 30 of those addresses are going to get wasted. So variable length allows us to more efficiently assign IP addresses closer to the number that are needed. So in the case of network B, I needed 116. I allocated 128. So there are going to be a couple of addresses, specifically 12 addresses, which I'm not going to use because I only need 116. In network D, it's a little closer. I needed 59, and I allocated 64, so there are 5 addresses that are not needed. In C, I needed 12. I gave it 16, so there were 4 extra addresses that may get wasted, but you know, also it will provide room for growth as well. I can add additional workstations or devices to those networks. And here in A, I needed 2 hosts, and honestly, 2 hosts are all I give it. Because if you recall, whenever we have a block size of any one of these, okay, it's always going to be the block size minus 2. Because I'm not allowed to use the network ID address and I'm not allowed to use the broadcast address for a host address. So in each one of these, it's going to be block size minus 2. So in the case of network B, it's 128 minus 2 gives me a total of 126 hosts that I will have usable addresses for. In the case of network D, block size 64 minus 2 gives me 62. So I'm going to have 62 usable addresses, 59 of which I can use right now. Okay. Network C, again, I allocate 16 minus 2 gives me 14, and I need 12. So I'm ultimately only going to have 2 left over. And then there's nothing for A. I mean, I needed 2. The block size was 4. So 4 minus 2 gives me 2. So that's exactly what I need, are 2. Okay. All right. Did I answer your question, or did I just blow right past that? All right, very good. Anybody else with questions? Shall we do one more VLSM? All right, very good. And let's just complete this. Then determine CIDR. Okay. So fine, we're going to do one more. And in this case, I'm going to basically tell you that I need network A is going to require, let's say 20 addresses. B is going to require 2 addresses. C needs 62 addresses. D is going to need 29 addresses. And E is going to need another 2. Okay? So now we've got 5 networks, although it really doesn't matter the number. So we're now going to, we've identified the number of networks, and we've identified how many hosts are needed for each network. Let me just move this over a little bit. Next, order the networks in the order of the number of hosts in descending order. Okay, so I'm going to borrow this. I'm going to do that. So what is my first network going to be here, Greg? Okay, it's going to be the 62, or network C, and that's going to be for 62. Sharon, do you want to do the next one? Okay, and that's D for 29. Patrick? What's the next network that I want in here? Okay. Okay, not quite. I'm not looking for CIDR. What I'm trying to do is, right now I'm on this rule right here. So I'm putting my networks in order of the number of hosts, with the largest at the top and then in descending order. So based on this, what is the next largest network that I need to list here? We put down C because that was the largest. Then the next was D at 29. And not quite. How about network A? Because that needs 20. Okay, there you go. Okay, very good. And then we need to have, let's see, where am I? 2 and 2. So I'm going to put B down for 2, and I'm going to put E down for 2. Okay? Okay, now we need to determine the block size, the maximum block size needed for each one of these. We don't want it too big. Okay, we want it just big enough to hold the number of hosts. So in the case of 62, what is the block size that is going to be needed? Okay, it's going to be 64. And one of the things that we want to keep in mind is that taking the block size, 64, minus 2 is going to give me 62 host addresses, which is exactly what I need for C. So this will fit C network perfectly. Okay? All right. Who wants to do the next one? Okay, so we're going to do 32 for the next. And again, 32 minus 2 gives me 30 usable host addresses. I need 29, so I've got 1 extra in this case, and that's perfect. And then finally, we've got the 20, and that's also going to be, yep, a 32. Again, 32 minus 2 gives me 30. I need 20, so this will work. And then finally, what are we doing for B and E? Block size of 4. We can't do a block size of 2 because 2 minus 2 gives me 0, no usable host addresses. So we need to do a block size of 4. So 4 minus 2 gives me 2 host addresses, which is exactly what I need for networks B and E. So we're going to do 4, and we're going to do 4. Okay, so now we're moving on to number 4 over on the left-hand side. Or no, I'm sorry, we've just determined number 4, which is your block size. Now we need to create our network IDs. So Sharim, what's our first network ID? Very good, 0. And Patrick, what would be my second network ID? Very good, 64. That's 64 plus the 0 up above. Okay? So I've got 64 here. And then Greg? Okay, 96. And then 96 plus 32 is going to give me 128. Okay? And then 128 plus 4 is going to give me 132. And then finally, 132 plus 4 is going to give me 136. And that's going to help me in calculating one of my broadcast addresses here. So now we're ready to go on and determine our first host address for each one of the networks. So here it's 1, then 65, then 97, then 129, then 133. And now we go to the broadcast addresses. Okay, so 1 less than the next network ID. So for this first one, it's going to be 63. Then we're going to do 95. Then we're going to do 127. Then we're going to do 131. And we're going to do 135 because I've got that 136 down here that's going to help me. And 1 less than 136 is 135. So I've got all of my last addresses now, my broadcast addresses. Now we're going to do the last address, which is always 1 less than the broadcast. So we're going to do 62, 94, 126, 130, and 134. And if you recall our rule that the network ID must be even, the first addresses all must be odd, last must be even, broadcast address must be odd. So as we look at these, we can see that the network IDs are all even numbers, that our first addresses are all odd numbers, that our last are all even numbers again, and then finally the broadcast address is all odd numbers. Okay? So the last thing we need to do is we need to determine CIDR. Okay? So, what is my first network going to be? Site or what? Okay, Patrick, you are correct. Okay, it's going to be 26. All right, because we didn't have the 128. And so if you recall, the block size 64, if we have a 64, let's just take a closer look at this. We said to begin with, okay, I really didn't tell you what address we were starting with. So let's just pick this one for kicks, okay? And what we said was we were going to have a block size of 64. Well, that means if I'm going to do a block size of 64, these two here are going to have to be subnets. So 8 plus 8 plus 8, 24 plus 2 more gives me a CIDR of 26. So we've got 26. And then we've got 32. And what is that going to give me a CIDR for? Okay, very good, Patrick. 27. All right, then another 32. So that's again another /27. Then we've got our /2 or our 4s. So that means it's going to keep, those are going to be a /30. Okay, how's everybody feeling with this? Okay, very good, very good. Shall we move on, or do you want to do one more Vlsm? I think you guys look like you've got the pattern down pretty well. So we will move on. All right. Having said that, let's just go back and let's take a look at the chapters. I'll quickly go through the first couple of chapters. And we were talking about internetworking and the basic networks. Now, the other night, I went over this, and maybe I'm going to do this again because okay. So this PowerPoint is actually a little different than the author's PowerPoint. I've beefed this one up. You might want to take a look at this a little closer about what's the difference between hosts and nodes and so on. Network links. And these are your nodes. So everything is a node. Okay. Generally, nodes are anything that's addressable. And I've got an X over this this hub because hubs are generally not addressable. However, you can purchase a manageable hub. You really don't see them anymore today. And then these are all of your hosts. Let me just go through real quick and see. This is a useful one right here. Okay. So one of the things that we want to know about is what are the collision domains. Okay. And what we're seeing here is this device right here is a switch. And every connection on a switch is a collision domain. So this switch has, if we go back and look at this switch has 4 connections to it. So here you can see we have 4 collision domains, 1, 2, 3, and 4. All right. So that's 4 right there. Again, routers, each connection to a router is a separate collision domain. So this router has 2 of its own, okay? So I've got 4 up here, and the router shares 1 with the switch. And then there's another one. So 4 plus 1 gives me 5. Now, what's this device right here, gang? What is this device? Anybody? That's a hub. Whenever you see a single arrow like that on the top, that's a hub. And all port connections on hubs make up one large collision domain. So you'll see that there are 3 connections to this hub, 2 for the PCs, and then 1 going back to the switch. That is a single large collision domain. Then again, what's happening is you're seeing that you've got a connection to the switch for the printer. That's a separate collision domain. And then we've got a wireless access point. Okay. All right. So the next thing you've got to figure out is broadcast addresses, okay, or broadcast domains. And broadcast domains are only broken up, okay, by routers. And Patrick, what is this? Can hubs have NACs? What is an NAC? Network admission control. I'm not aware of hubs having that, okay? In fact, I'm not quite sure. Network admission control, describe. Oh, network, do you mean network access control? Because that's something completely different, and no, hubs don't do that. Okay? Hubs don't do that. They don't have the intelligence for that capability. Okay? Hubs are very simple devices. All right. Moving on. Let's see what I've got here. Okay, this gets back into what the author was talking about, a very basic network where you have a hub. In this case, based on this diagram, how many collision domains are there? There is only one, okay? A hub, all connections to a hub create a single collision domain. All right, so here's another one. Here we have 2 switches and a router. So how many collision domains do we have? Okay, careful, Sharon. Remember, with a switch, okay, Patrick, you are correct. There are 6 collision domains, okay? Because every connection to a switch is a separate collision domain. So I've got 1, 2, 3, 4, 5, 6, okay? And yes, Sharon, you're correct. There were 2 broadcast domains. And again, the only thing that can create a broadcast domain is a router. Routers break up broadcast domain. So there are 2 connections to the router, a broadcast domain for each one. Okay? So 2 connections to the router, 2 broadcast domains. Okay? All right, very good. So shall I then bring up, let's test you out and let's see how we do here. Let's do files. Close this down. Graphic images. And scroll on down here. And we'll use I think they're all pretty much the same. Okay, so if A, B, and C are all hubs, how many collision domains, how many broadcast domains? A, B, and C are all hubs. How many collision domains, how many broadcast domains? Okay, very good. One collision domain. And Patrick, 1 and 1. You are correct. You are both correct. Excuse me, gang. I think it's time for another cup of coffee. All right. Let's now move on. If A is a switch and B and C are hubs, then same question. How many collision? How many broadcasts? I'm going to put you down. I'm going to set myself up for another cup of coffee. 1 second. Maybe I should have some soda instead of coffee. All right, so that's going. All right, so A is a switch, and B and C are hubs. So Sharon is going to go for 4 collision domains. Okay? Greg you're saying 2. Okay? And let's see, Patrick, what are you saying? Okay. So the correct answer here is 2 collision domains and 1 broadcast. 2 collision, 1 broadcast. Again, the only thing that can separate a broadcast is a router. And A is a switch. B and C are hubs. Okay? A is a switch. B and C are hubs. So as a result, you've got a broadcast domain over here on the left side and a broadcast domain on the right side. And again, with collision domains, you've got a collision domain on the left and a collision domain on the right. Okay, so next. A is a hub, and B and C are switches. A is a hub, B and C are switches. Okay, so we're kind of reversing it a little bit. How many collision, how many broadcast? Okay. So again, yes, there is only 1 broadcast. That I agree with. However, I'm seeing a little confusion on the number of collision domains. Okay? Take a closer look, because no one has gotten the answer correct. Okay, there we go. Yes, Sharon. So, Sharon, you started off by saying that there were, how many did you say? I think you said there was like 6 collision domains. All right. So do you now see where that 7th collision domain is coming from? Okay. So again, B and C are switches. So every connection to a switch is a separate collision domain. So I've got 1, 2, 3 on the left, 4, 5, 6 on the right. Then up above here, A is a hub. So every connection to that hub is a single collision domain. So I've got 6 down below, and I've got this one larger collision domain at the top. So that gives me a total of 7 collision domains. Okay? Now, question, are there any routers in this diagram? No. Therefore, if there are no routers, this is all one big broadcast domain. So 7 collision, 1 broadcast. All right, very good. Let's step it up a bit. Okay, so A is a router, B is a switch, and C is a hub. Okay, take a moment to think about that. Let me mix up my coffee. I would make a horrible Starbucks customer because I live on instant coffee. I don't think I've gotten bad enough to just swallow the instant coffee powder, but honestly, the only thing I'm really looking for is the effect. Okay, so we said that A was a router, B was a switch, and C was a hub, correct? Okay, A router, B switch, C hub. Okay, very good. So 2 broadcast domains, correct? And 5 collision. Well, let's take a look at this, okay? So I've got a B is our switch. So I have 1, 2, 3, 4, okay? Collision domains. And then on the right side, C being a hub, that's 1 big collision domain. So there are 5 collision domains. All right. Looks like you all got this one, okay? I will be asking a couple of these questions, maybe 2 of these questions. Okay, gang? So it looks like you are prepared. So I'm happy about that. Any questions? Shall I move on? Okay. I'm going to move on. So we'll close this. We'll go back to home. Go to our PowerPoints. And as we look at Chapter 2 here, data encapsulation, Ethernet networking. All right. See, anytime that you'll see that some of these things I've actually modified from the author. Okay, so they get in a little deeper. Okay. Anyway, we went through all of this. Know what the difference is between full and half duplex when we talk about switches and hubs. Switches provide, for the most part, provide full duplex, okay, because they have the intelligence to handle that. Hubs, however, only perform at half duplex, okay? And any connection to a hub is going to be running at half duplex, which is what you're seeing here. Here is your standard MAC address. So this is, again, a figure that I might throw up there, and I'll ask you, okay, what is this? All right. I may not say that it's a MAC address, but as you can see, it's 48 bits long, okay? And this OUI, or Organizationally Unique Identifier, this identifies the manufacturer. An example would be Cisco. And then Cisco assigns these 24 bits here. Here is your typical Ethernet frame, okay? And again, one of the things you're looking for is this destination and source address, which is 6 bytes long. All right. Know your different types of cables, okay? Also, your straight through, your crossover, and your rollover. Okay, those are pretty simple. And again, that's a lot of review. We had that in 143, so most of you should be in pretty good shape there. This is a typical crossover cable. And then these are the typical cables that we use. We use either a crossover for switch to switch and for router to router or router to PC. Now, one of the things that I want to say here is that this is kind of old school, okay? Most of today's devices, routers and switches, are auto sensing. In other words, they're able to figure out whether or not they need to be crossed or uncrossed, okay, straight through or crossed. So you can just about use any type of cable. You can use a crossover cable, you can use a straight through cable, and the devices will figure it out on their own. Only the older Cisco devices do you need to be specific with the cable. Let me just give you an example. Okay, so let's pull out we're going to pull out this router here, and that's a 1941. You'll see that it's got 2 gigabit connections here, Ethernet gigabit, and we're going to pull out a PC, and then we're going to try to connect this, okay? And I'm going to use a straight through cable. Straight through patch cables are what we generally use in networking. And one of the things that we're going to notice here, this is on the gigabit 00. Let me just go in and configure that real fast. So, and so that's int gigabit 00. And we are going to IP address 192.168.0.1 with a 255.255.255.0. And then we're going to do a no shut. Okay. Now, you'll notice that the whole thing came up. Okay. And so back to this. Okay. This is saying for a PC, I'm going to move this away. Going from a PC to a router, you should see a crossover cable. And here what we're seeing is that a straight through cable worked just fine. Not a problem. Okay? Let's remove this. It shouldn't have worked. Okay? It shouldn't have worked based on the documentation, but that's kind of old. So let me get rid of this. Now let's try a crossover cable. Again, gigabit 00 over to our PC, fast Ethernet. And notice that that one works. Okay, they both worked. When the documentation here tells us that in the case of a PC to a router, we should use a crossover cable. Well, we saw that both a crossover cable as well as a straight through cable works, and that's because the newer Cisco devices are auto sensing. Okay, they will figure it out. It doesn't matter what kind of cable. That's why for the most part, you don't see crossover cables anymore in data centers. Okay, we use all straight through patch cables. Okay. All right. Now, quite frankly, because of this confusion here, I am not going to ask you one of these questions. Okay. It just creates too much confusion. But you should be aware, if you go on for your CCNA, you should be aware of some of these rules. Okay. All right. Let's see what we got here. Okay. Moving on. So that's chapter 2. Everybody knows about all of our different types of console connection and VTY, so I'm not going to go through that. We know about data encapsulation, okay? How the transport layer gets encapsulated into the network layer, into the data link layer, and so on down the line. And we've got this thing called segments, packets, frames, and bits. And again, if we go into, let me find my other diagram. Okay. Again, this is really what you want to review, because this kind of puts it all together. It talks about all of the different layers. It talks about the protocols that are being used in each one of the layers. It talks about the PDU, and again, down below, PDU is equal to protocol data unit. So at the transport layer, it's either segments or datagrams. It's either packets, in the network layer, and it's frames or cells in terms of something called ATM in the data link layer. But Ethernet uses frames. And then in the physical layer, we've got bits. Again, you should also be aware of where do we use different types of addresses. So port addresses are used up in the transport layer. IP addresses are used in the network layer, and MAC addresses, as in frames or Ethernet frames, are used in the data link layer. Then devices. So what is the highest level that a device communicates at? Hubs only communicate at the physical layer. They don't go any higher than the physical layer. Switches communicate at both the physical and data link layer, but no higher. Routers take it one step up. They communicate at the physical, the data link, and the network layer. Then you've got firewalls, which communicate in the first 3, physical, data link, and network, and also communicate at the transport layer. But it's only the hosts which communicate at the highest layers, okay, of the OSI or TCP/IP model, okay? And generally, with respect to TCP/IP or the DoD model, this is generally referred to as the application layer. Okay, this whole big thing is the application layer. And hosts live in this application layer. None of the other devices go this high. Otherwise, they're not really that type of device. They've got a lot more functionality than just a firewall, router, switch, or a hub. Okay, does that make sense, gang? All right. I will share this PowerPoint with you all, with the class, once we finish up. Okay. Okay, so one of the topics that the book discusses, and I don't recall if I have a question for this, but something that you should know is that the Cisco hierarchical model, and the hierarchical model in Cisco has 3 layers. The access layer, in which devices such as hosts connect to the network. And generally, they're connecting to switches. Next, you've got the network layer, in which the different networks are interconnected. Okay, the subnets are interconnected through the routers. And then finally, you've got these, the Cisco or the core layer, and which you're going to find up above. Okay. So the core layer provides an optimized, reliable network structure based on forwarding traffic at very high speeds, and these are core layer switches. So packets moves the packets as quickly as possible. So the core layer really focuses on speed. Okay, it's not interested in security. It's not interested in really the needs of the individual hosts. It is simply focused on moving data through the network as quickly as possible. In the distribution layer, however, which is handled by routers, we have various control mechanisms which allow us to implement our kind of our first level of security. Not really, because even in the access layer, we do have some security capabilities. All right, but primarily, most of our security is implemented through the distribution layer. And then finally, the access layer. All right. Well, again, this provides access to the end users and their devices, such as PCs and servers and so on down the line. All right. Okay. So we've got that taken care of. Where am I? Here I am. And we get into chapter number 3. Okay. Again, we talked about the DoD versus the OSI model. And again, this upper layer, which consists of the application session and presentation layers, is often referred to as the application. Transport, host to host, network, the internet layer, and then finally the network access layer is the data link or physical. And again, you see some of these. Again, all of this is kind of tied back into this thing here, okay? So if you study this, you'll be in pretty good shape. All right. You should be familiar with the different protocols. Not only familiar with the different protocols and what they do, but also what port numbers do they use. Okay, I will be asking about port numbers, so make sure that you know your port numbers, please. All right. Okay. Secure Shell, we really didn't get into Secure Shell. I will get into that next semester. So there will not be any questions on Secure Shell. Well, I take that back. I may ask the question as to what is Secure Shell, and that's information that's provided in Chapter 3. I won't go into how do you configure Secure Shell. That is something that we will do next semester. FTP, again, that's something we will worry about later. You should know that it is one of the protocols. You should know what port addresses it uses or what port numbers. Okay, TFTP, the same thing. We did get to actually configure TFTP, so you'll want to know that as well. Okay. All right. Yes, and we went through that, and all of these. I'm not going to go through these now because you should pretty much have this stuff down. Now, this comes to our diagrams. You should know these diagrams. So this is first a TCP segment. This lives in the transport layer, okay? And the thing that is going to key you off here is first, notice these 16-bit source port and destination port. So those are the port addresses, and they're 16 bits long. So when I say that HTTP uses port number 80, okay, we're talking about that 16-bit source port or destination port, and it's going to have, if it's the destination, it's going to have the value 80 in it, okay? The other thing that's crucial in a TCP segment is that it has sequence numbers. if you recall, TCP is a reliable transport protocol, unlike UDP, which is often referred to as unreliable. It doesn't mean that we don't want to use UDP, but UDP gets used for different purposes. But if we want to ensure delivery of our data, which most of the information that rolls across the network, the internet, is going to be TCP segment type information. Okay, so look for that 32-bit sequence number. And by the way, that is not to be confused with a 32-bit IP address. Okay, so watch out for that because both of them are 32 bits. This is a UDP segment, again, part of the transport layer. But now you'll notice that the 16-bit port addresses are here, but there is no acknowledgement fields. There are no 32-bit acknowledgement fields. And for this reason, okay, UDP is a lighter protocol. It tends to be, it doesn't have the overhead, doesn't have the bulk of TCP, and therefore it tends to be a little quicker, more efficient, but it's not as reliable as TCP, okay? So that is your UDP segment. And again, going back to our diagram, this diagram here, again, you see your segments and you see your datagrams, okay? And TCP and UDP in your transport layer. All right. Sweet. Okay, so Patrick stepped out for a minute, and the recording's still going, so we're good. Okay, everybody doing good? All right, so let's take a look. Here is an IP packet. And again, you'll notice a source IP address of 32 bits and a destination address of 32 bits. Okay, this is the network layer. And again, we'll go back to this diagram and you'll see we have packets. Okay, and the addresses are IP addresses. So here you've got source IP, destination IP, 32 bits, not to be confused with these 32-bit sequence numbers or acknowledgement numbers. Okay, this is a segment. This is a packet. Okay, so keep those clear. All right. So know what, again, know what your different protocols are. Know what ARP is. Okay. We're actually going to get in next semester and take a very close look at what ARP does. So right now, you're going to read this in the book, and you're still probably going to be scratching your head as to, okay, well, what does ARP really do? Well, we're going to get into it, and you're going to see it in detail. So by next semester, you're going to have a solid understanding of ARP. All right, so that's chapter number 3. Where am I? Here. Chapter 4, I'm pretty sure chapter 4 gets into static IP addressing. Let's just take a look at this real quick. So we get in, yeah, and we're talking about IP addresses and so on. We talk about subnetting methods, okay? So these are some additional notes that I have. I have gone through all of this stuff with you. All right. We talk about broadcast or network ID versus broadcast addresses and so on, okay? If you want, you can look through this. But I think we all now understand how to do fixed length subnetting. And that's what this chapter is all about. All right. Chapter 5 is on variable length subnet masks. or maybe not. It may still be on fixed length. No, it's VLSM, variable length subnet masks. And I think we all have a solid understanding of that, okay? How about summarization? Does anyone have any questions on summarization? Any questions on summarization? Okay, I'm not hearing anything, so I'm going to assume we do not have any questions. Okay, Patrick, you're back. Patrick, any questions on summarization? Or did you feel comfortable in our discussion a couple of weeks ago on what summarization was all about? Okay, so one example. Let me go through this. This one is not so good. This one is very good, okay? If we look at this, okay, you've got all of these networks over here. And the objective of summarization is to simplify the routing table such that the routers are able to quickly make a decision as to where to forward a packet on the network, okay? So rather than having routing table entries for 5 different networks, 172.1.4, 172.1.5, 1.6, 1.7, and 1.4.128. Rather than having 5 separate entries, can we summarize all of this into a single entry such that the router can quickly determine that if that packet is coming from any one of these 5 or going to any one of these 5, that we can summarize any of this, okay? All right. So what you need to do is you need to identify what is common to all of these addresses. Well, if you look at these network IDs, you can see that 172.1 is common to all of them. So that is not our focus. Our focus is actually on the third octet. So for this network, the third octet is a 4. This network, the third octet is a 5, 6, a 7. And then this network over here is further divided. So we have a 4.0 and a 4.128. And we can see that the 4 is actually subnetted further, such that each one of these networks has 126 hosts or possible hosts in it. So what we're going to do is let's pull up our notepad here. And what I want to do is we said the 172.1 is common to all of them, okay? It's the 4, 5, 6, 7, and the 4.128 that is uncommon, okay? That is different for each one of these networks. What I want to do is I want to look at this third octet, and I want to look at it in binary, okay? So if we look at 4, 4 is actually equal to 1, 2, 3, 4, 5, 1, 0, 0. 5, 1, 2, 3, 4, 5, 1, 0, 1, 6, 7. Okay. And then finally, we've got the, and actually, if you look at the 4.0, okay, what you've got there is we're looking at that extra bit. And down below the 4.128, the network ID there is this, okay? Now, what I'm looking for when it comes to summarization, I'm asking the question for all of these networks, for these 5 networks, which bit pattern is common to all of them? Which bit pattern is common to all of them? And to answer that question, it is going to be the first 6 bits here are common to all of them. 5 zeros and a 1. Okay? 5 zeros and a 1. That is common to all of them. And if you ask what that value is, if we go down here and we say, okay, we said that was common to all of them. And I'm going to simply add zeros on the end. So what's common is if I use the summarized address for these 5, and I say 172.1.4, because that's the value that we have right here. That's 4.0. That network ID summarizes all 5 of those addresses. Okay? Questions? Questions? Everybody okay? Patrick, how do you feel? Okay. All right, very good. Okay. That brings us to chapter 6. And this is the Cisco's iOS. All right. Now you know how to configure. You know what the CLI is. Okay, there's nothing there. You know what the user exec, the privileged mode, the global configuration mode. We've talked about all of this, and we've honestly been talking about it since almost the very first class, because I like to get into it immediately and get you comfortable with it. Some of the different editing commands, it's always a good thing to go through and just review these. Router command history, again, just review some of this, okay? From time to time, I may have a question in there. We've talked about host names. We haven't so much gotten into banners, but banners are simply messages that appear at the different prompts. And so take a look at your book if you want to come up to speed on those. They're very easy to set up. The passwords, again, we've been working with passwords since the very start of the class, and those interface descriptions we addressed kind of midstream. Okay. Again, here's a little coverage on the host names and the banners, and don't hesitate to go in and just play with this in Packet Tracer. It's very easy. Passwords, we covered VTY, console, SSH. I am not going to get into talking about that. Using descriptions, description WAN to Miami. Okay, and most of you have used descriptions before. Some of the different commands that we use for verifying interfaces. You should really take some of these commands and put them in your command files. If you recall, I want everyone to come into class, for the exam, and I want you to have that command file. And the more stuff you've got in there with some notes and so on, the more quickly you will get through some of this stuff. Okay? You know how to bring up an interface. You know how to configure serial interfaces. One side gets a clock rate, the other does not. The DCE side gets the clock rate. The DTE side does not. Okay. Looks like we lost Sharon. All right. Well, she kind of went through this the other night. So this is really review. All right, very good. All right, so view, saving, and erasing configurations. That was kind of part of the last lab that we had, showing how to the startup as well as the running configuration. And again, you've been doing that through the semester. And this That was a weird slide. All right, so let's get out of this. Let's close this down. Let's go to Chapter 7. And Chapter 7 is where we get in talking about the password reset. And Greg, that was the one topic you wanted to just go over. Okay, so again, know what the different components, the different types of memory, the different operating system levels that we have within a Cisco router or a Cisco switch for that matter. Okay, showing the current configuration and copying TFTP, which was part of our last lab. Okay. Erasing the configuration, configuring DHCP. Again, make sure that you've got those command examples in that file on a USB drive so you can quickly bring that stuff in. Okay, and we talked about helper addresses. syslog, NTP. Okay. All right, maybe it's, oh, okay, yeah, it's in Chapter 8, that what Greg is looking for. So let's close that. Here we go. The key to the password reset, okay, to get in is to break into the ROM monitor, and reset, okay, the configuration register. Let's take a look at that, okay. So here's the configuration register, and it is a 16-bit register. And you can see here are all the bits. Each one of these bits does something, okay? They're like little switches, okay? And here you can see the configuration register, the default configuration register has a value of 2102. Okay, so 2102, and then we see the binary down here. Well, one of the things that we want to do is if we want to bypass, okay, the processing of the startup config, we want to actually set this value from 2102 to 2142. So if I change this 0 to a 4, that means down below here it's going to be, hold on, where am I? It's going to be 0, 1, 0. Or I'm sorry, 7. 0, 1, 0, 0. Okay, those 4 bits right there. 0, 1, 0, 0. And that's going to change that to a 4. But thankfully, we don't have to work on this in binary. Okay. Yeah, and this is something else that we showed in 8 about flashing the drive. And I'm not going to hit licensing. Oh, dear. I thought I had this. Oh, I know where I had this. Okay. Oh, here it is. I think this book is in our config register. Right, here it is. Managing the config register. So what we want to do is we want to go into ROM-MON, and we want to change it from 2101 or 2102 to 21.4. Or, yes. And so let me just demonstrate this real quick in Packet Tracer. And we'll bring Packet Tracer over. Go into our router, say EN, and show version. And at the very bottom of this, okay, you can see that the current register, its default value is 2102. And we want to change it to 2104. And the way we do that is we cause the router to reboot. And the easiest way to do that is to simply tell it to reload. So I'm going to say reload. I'm going to say yes or no. Has been modified. Do we wish to save it? No, I really don't care. And are we going to confirm the reload? Yes, we are. And once it starts to reboot, I'm going to hit Control C. So there it's rebooting, Control C. And we're now into ROMmon. So ROMmon is a low-level operating system. The router is not fully up just yet. And what we're going to do, we're going to say config, and we're going to say 0x2141 or 42, okay? And then we're going to say reset. So this is again going to force it to reboot. And we're going to allow it to reboot. Now, because of the 4, changing that value to a 4, it will now bypass the startup config. And you can tell that because of this prompt right here. That prompt tells you that it's not reading the startup config anymore. And because it's not reading the startup config, it's not processing the passwords that we may have set up, such as our enable password, our secret password, our V2Y, or our console passwords. None of these passwords get processed. So when the system does come up, and I'm going to say no to this, when the system does come up, it comes up like it's a brand new router. And when I go in, and I'm now in privileged mode, and we're going to do a show us the version, and you'll now notice that at the very bottom, you see that the configuration register has been reset to 2142, which means do not process the startup config and all of its passwords. Now, if I had passwords in here, at this point, because I'm now allowed to get into the router without any passwords, I can go in and reset whatever passwords I've forgotten. Then the very last thing that I want to do is I want to do, well, next to the last, is I want to do a copy, run to start. So I want to copy the running config to the startup config, okay, to save the new passwords that I've now put in. And then the very last thing that I want to do is, and we'll just press enter on that, I'm going to go into my global configuration, okay, and we're going to pump in configuration register, and now it wants to know what value do you want, okay? So we want 0x2102. We are now changing it back from 2142 to 2102. Press enter. And now that's set. And if I do a do show, remember do because I'm in the global configuration, do show, and let's look at version again, and we're going to see that it has been reset from 2142 to 2102, okay? And now if I do a reload, all of the passwords, the new passwords that I've put in will now take effect, and the system will come up and it will be asking me for passwords. So, Greg, does that pretty well cover it for you? Okay, very good. All righty. See, this is my old book for this course. And it actually goes over 2 semesters worth of information. You'll notice if you look at this book, you'll see that a lot of the examples that we have in our current book came from this book, okay? And that's why I still refer to this this book. It's a good book to have, and I'm pretty sure that I've actually got it in the site. I generally give it away because I've got it in a PDF. Let's go to the site. Hold on one second. There we go. And let's go back to, I'm going to go to Pages, and I think it's Supplemental. No, I don't have it in here. One second, maybe. Okay, remind me to send that one out to everybody. PDF. Let's pull up that. I also like this this textbook simply because it's in PDF and it makes it very easy to search the entire textbook. Okay, so if you're looking for a particular topic like DHCP, you know, it'll get you right into the sections that you need to know. So I will include that as well. Let's go back. Let's go back to our PowerPoints. Chapter 9, it goes into routing. So in this chapter, it's important that you know what is the difference between a static route, a dynamic route, and a default route, okay? And I think we did pretty well the other day going through all of that. That's pretty recent stuff. Okay, so show IP route, that's how we display our current IP routing table. Okay, and then we've got our, one of the things you might want to do is just read through this to get a general understanding of how the routing process works. And again, you want to know about your static routing, your default routing, and your dynamic routing. Dynamic routing is handled by routing protocols such as RIP or IGRP or EIGRP or OSPF. Those are some of the more common routing protocols that you're going to run into. RIP is the one that we've been using throughout the semester. Static routing, you have to use an IP route command, and default routing, whenever we don't specify a route and the system is looking for an unknown network, okay, it knows the network, but it doesn't know how to get there, then we use the default route. So again, your static route, that command is IP route, destination network, the mask, and then select either the next hop address or the external interface. And then we have the administrative distance, and we said that different routing protocols or different definitions have different administrative distances. The lower the administrative distance, the more relied upon that particular route is. So the router will look at any directly connected network, okay? That gets an administrative distance of 0, the lowest value you can have. Next is a static route, and that gets a value of 1, okay? Generally, unless we specify an administrative distance other than 1, okay? Let's see if we have that in here. Yes. So here are some of the different administrative distances. So you've got connected interface is a 0. A static route is a 1. Then if you're using EIGRP, It's a administrative distance of 90, OSPF 110, and notice RIP is at 120. So of those three routing protocols, EIGRP, OSPF, and RIP, the router relies on RIP the least, okay? So it will use RIP if it has to. If there's nothing else available, it will use RIP. But if you have both RIP and EIGRP, it's going to look at EIGRP before it looks at RIP, okay? Because it finds that the information from EIGRP is more reliable, okay? I just want to go back real quick to the static routes. So again, here's an example. You've got IP route. You specify the network ID, and you notice that 0 right on there with your subnet mask of 255.255.255.0. And then we're specifying the next hop address, which in this case is 192.168.2.4. Okay, the other way that we can go is we can specify, here you see the same thing as above, only we're specifying an administrative of 150, which means that if I'm running RIP, which gets an administrative distance of 120 by default, RIP will take precedence over this static because of the 150. And then finally, we've got this static route, the network ID, the subnet mask, and this is the exiting interface on the router, so S000, okay? All right. Again, the default route, IP route, 0000, and a subnet mask, 0000, and then the next hop address. So what this is doing is it's telling the router this is the way out to the internet, okay, for any networks that you do not know. If you don't have an entry for a particular network, this is the path we want you to take. And all of these zeros are basically saying, look, I don't care, okay? You know, send it out through this route, through the 172.16.10.5. Know the difference between your routing protocols, distance vector, link state, as well as hybrid. So a distance vector routing protocol is RIP, the one we've been using. A link state would be something such as OSPF, and then a hybrid would be EIGRP. All right. So let's look at Chapter 10. Chapter 10 talks about switches. Again, you should know how the switch works in terms of forwarding and filtering and broadcasting addresses, okay? And how it builds the MAC table. And again, most of that is based on the source MAC address, the source MAC address. You should read through this process and make sure that you've got this process down. Okay. Port security, be familiar with the different commands, your different port security commands, and here they are here, okay? So your options for switch port security would be aging, MAC address, maximum, as well as specifying the violation. Okay. All right. We talked about broadcast storms and how switches use STP to avoid a broadcast storm, which is what you saw here. Okay. Also, your show MAC address table, as well as show the VLAN interface and the IP interface. All right, guys. Wow, 2 hours. Any questions? Any questions? Okay. Very good, Patrick. Greg, you good? Okay. Maybe Greg stepped away. All right, no problem. What is the game plan for this Thursday's class? We will not have class, okay? Use it for a study session, okay? You are always welcome to call me and, you know, with any kind of miscellaneous question you might have. Also, as far as the class party is concerned, we're pushing that off to Thursday. So both the 244 as well as the 235 class, because half of our class is in both of those classes, we're going to just have one big pizza party next Thursday, not this Thursday. Next Thursday, I believe it's the 12th, okay? And probably around 6 o'clock, okay? Because I need to give everyone sufficient time to get their packet tracer done. I'm going to be putting out a message with regard to, you know, what all is in the final, as well as what you should be bringing and what you will be allowed to do. I will also be sending out these files that I've mentioned. One will be that PowerPoint presentation, Greg, you were asking about, also that book. And I'll also, as soon as the video for this evening's review is completed, I will then upload that to YouTube, and we'll get that online, and anybody who cares to can look at that. Okay? All right, guys, are we good? All right, excellent. No problem. Glad you could come, and I will talk with you all soon, okay? I'm going to go grab some dinner and wait for this video to finish up, and then I will get that up as quickly as possible, probably later tonight. Okay? Thank you, guys. Have a good night.